All right, a one-sample t-test is another basic inferential statistical test. It tests the assumption that a sample came from a given population. So let's dive into this. Now, when you're conducting a one-sample t-test, there are several things you need to know. Specifically, you need to know the population mean, the sample mean, the sample standard deviation, and you need to know the sample size. Now let's work through a hypothetical example. Let's say that we're working for a brewery, and this brewery is growing its own barley. And when they're growing their own barley, they happen to know that they get a mean of 5 bushels per acre. However, there's a new technique that they want to try out. They want to see if, could it be better? So they give you 30 acres to try out this new technique. You find that in these 30 acres, you actually get a mean yield of 7 bushels per acre and a standard deviation of 4 bushels per acre. So we have all the information we need to know to calculate a one-sample t-test. We have the population mean, we have the sample size, the sample mean, and the sample standard deviation. Now, if we're going to go about calculating and running this one-sample t-test, there are several things that we need to do. We'll need to state our hypotheses, set our rejection criteria, then calculate our test statistic, interpret our test statistic, and then I'm going to add another step where we need to report our findings. So let's tackle that first step, which is stating our hypothesis. And again, these are not the scientific hypotheses. These are the statistical hypotheses this one-sample t-test will actually test. Specifically, the null hypothesis, which states that everything's coming and is due to random chance. So this mean of 7, the reason it's not a mean of 5 is just sampling error and random chance. It's really coming from a population with a mean of 5. And the mutually exclusive and exhaustive alternative hypothesis that it is not coming from a population with a mean of 5. Now that we've got our hypotheses stated, the next thing that we'll need to do is actually set our rejection criteria. All right. So when we go about setting this rejection criteria, it's important to think about our test statistic. In this case, our test statistic is going to be a t-value. So let's go ahead and sketch the sampling distribution of the t-statistic. Now, one thing we know is that this sampling distribution is symmetrical about 0. So just pretend that I drew that perfectly symmetrical. Okay? And we also know that it varies depending upon the degrees of freedom. For a one-sample t-test, the degrees of freedom is n minus 1 because we're calculating an estimated variance based on n scores, and there's only one estimate, so it's n minus 1. So 30 minus 1 to get us 29. Now, from that point, you would actually need to go to a table in the back of your textbook and then look up the t-critical value or use R or Excel or some other method. Now, we have a two-tailed situation because we're saying equal and not equal to. It could be greater than, it could be less than. So we need to find the critical values that bound our critical region where our alpha level, and let's say we're working with an alpha of 0.05, which we already indicated is two-tailed. We need to figure out what that value is. Now, I'm not going to show looking up through the table because, copyright or something like that. So I already looked it up, and it's 2.045 and negative 2.045. So if we have an observed t statistic which falls either in this critical region or in this critical region, we would reject the null hypothesis. Now, we can state this quick and easy using absolute value to give us sort of a verbal sort of spelling of our rejection criteria. So, if our t observed, specifically the absolute value of t observed, is greater than the absolute value of our critical values, then we reject our null hypothesis and accept the alternative hypothesis. So we've got our rejection criteria all laid out. Now it's time to go about calculating our test statistic. Now, when we're going to calculate this test statistic, first thing that's going to help you out a lot is to actually look up the formula. So the formula for t observed in a one sample t-test is our sample mean minus the hypothesized population mean divided by the estimated standard error. Now, we have, looking back, our sample mean already. That's 7. We have our population mean already. That's 5. We do not yet have our estimated standard error. However, the estimated standard error is the sample standard deviation divided by the square root of our sample size. So we have this value. It's 4. We're going to divide by the square root of our sample size, which is 30. So 4 divided by the square root of 30, the square root of 30, rounding to 2 decimal places, is 5.48. Now, for the sake of clarity, I'm going ahead and rounding to 2 decimal places in this answer. However, if you're calculating this out, don't round until you get to your final answer. So 4 divided by 5.48 gets us 0.73, rounding to 2 decimal places. So then we can go ahead and substitute this value in back up here. So 7 minus 5 is 2, divided by 0.73 gets us 2.74, rounding to 2 decimal places. So we've calculated our test statistic. Now it's time to actually interpret our test statistic. All right, now looking at this, we already essentially laid everything out, so what we really need to do is essentially fill in some more values. So our t observed, and specifically the absolute value of our t observed, was 2.74, which does in fact happen to be greater than the absolute value of our critical value for t, which was 2.045. As a result, we reject our null hypothesis and I'm not going to have to rewrite that. Accept our alternative. Now, what does this tell us? It tells us that our sample mean of 7 is not likely to come from a population with a mean of 5. In fact, it is so unlikely that we are rejecting that possibility altogether. So, what does that mean? Now, you have to interpret this in the context of the research design. Ultimately, this is a quasi-experimental design with one group and only a post-test. As a result, it is consistent with the notion that the new technique caused an increase in yield per acre of barley. However, it does not outright prove it. Now, we're getting to the point where you need to practice reporting your results. So this is really the next step. And indeed, if we were hired by a brewery to run these statistics for them, we would need to report these statistics to them as well. Doing this. So it looks like we could write something like this, where the yield per acre, now we throw an M for our mean, and then we report our standard deviation. Notice that the abbreviation that I'm using for standard deviation is different in APA style. Was significantly greater than 5. Now, notice that I don't say anything about rejecting the null hypothesis. If it's statistically significant, then that's essentially jargon for rejecting the null hypothesis. After we state that, a comma, and we need to actually report our t statistic. Now, when we report this test, APA has a very specific format. We need to write t to indicate we ran a t-test. Then in parentheses, we need to specify the degrees of freedom, which in this case was 29. Then we need to actually report our observed t-value, which was 2.74. Then we need another comma, and then we need to make a p-value statement. Now, a p-value is the probability of getting this observed test statistic. Note that we did not calculate an exact probability for that. What we did is we found the t-value that would have a two-tailed probability of 0.05, and then found out that our t observed is actually more extreme than that. Therefore, its probability has to be less than 0.05. And so that's how we're going to report it. The probability of obtaining our test statistic was less than 5%, or 0.05. And at its most basic, that's how you would report the results for this test.